Hello everyone. Now the lecture here that we'll be discussing about is basically frequency response. So experiment 2, frequency response. So what I told you in the earlier lecture, that any plant can be defined by two two factors: plant gain and the time constant. If the gain and time constant of a plant is known, we can mathematically model the plant, and we can know for what value of input what is the kind of the output that we'll be getting. In the earlier experiment, we learned about the ways of finding this plant gain and tau, that is time constant, in time domain analysis. In this case, we'll be learning to measure the same in frequency domain analysis. So the target of this experiment is same as before. We'll be finding Kp and tau. Just the changes will be finding these things in frequency domain. Now, while working with frequency domain, we need to provide a periodic wave or periodic input. So the input that we use is sine wave, and the advantage of using sine wave is a natural phenomenon. For example, you can maybe you can see sine wave everywhere. For example, if you pluck a guitar string, that will create a sine wave, that is a single frequency tone. So sine wave is very natural phenomena, and inside a linear black box, this is a linear black box, which is our servo system. It can be anything. Again, I'm saying it can be any plant. So for our experiment, this is servo system. So if we provide a sine wave as an input to our linear black box, we get a sine wave as an output. So for sine wave input, we get sine wave output. Now, what is the difference between input and output? Suppose if this is the input, mm, maybe the output would be something like this. So what is the difference? The difference, there is only one difference, that is only two difference. First is there will be a change in magnitude. Second is there will be phase lag. The phase lag, we define it as phi, and there is change in magnitude. So from this change in magnitude, we'll be able to determine the gain, and from this phase lag, we'll be able to determine tau or time constant. This is true for any linear black box. That is for any linear plant. If we provide a sinusoid as input, we'll get a sinusoid as an output. And if both input and output are sinusoids, the magnitude will be shifted and there will be a phase lag. There may or may not be a phase lag. And from that from the value of change in magnitude and change in phase, we can determine the plant gain and time constant. So in this experiment, we'll be looking at that. So let us move to the software at the beginning. So from the software, we'll go to File, Load Setup, then we'll load experiment CA06P04. Let us just look at your lab sheet at first. Triple 306 hardware lab sheet experiment 2. So if you look at the lab sheet, the first thing, we go into the setup box and we compare it. So in the setup box, it said that CA06P04, we have selected it. Controller is open loop. That's also there. Signal is sine there. Level is 60% there. Offset 0. Frequency is 100 millihertz. Reference internal. So everything is as it should be. Okay. Since everything is as it should be, now what we need to do is, if we look into the data sheet, we need to change the frequency. After changing the frequencies, we need to find the output volts from peak to peak, and we need to find the phase lag, and from there we'll be finding the amplitude ratio, and we'll be finding amplitude ratio in dB. I'll be telling you how to do this. Firstly, say this is 100 millihertz. So at first we don't see any output. It's a glitch of the software. We have to increase and decrease, and we have to change the frequency one time, and as a result you will see 100 millihertz sine wave. So this sine wave over here that has peak at 90 degree, this sine wave. So this is the x-axis is in degrees now. This is 180 degree. This is 90 degree. So the sine wave that has a peak at 90 degree is actually the input, and the lower peak valued sine wave is the output. Now, as we can see, there is a change in amplitude, and there is also a phase lag associated with it. One thing is to be noted that the difference between step response and response is that in response, you gradually increase the voltage, it reaches a peak and then gradually decrease. So as a result, you will see the smooth transition in the values of in the speed of the motor itself, servo motor itself. But if we consider step response, it it takes a value and suddenly changes to another value. So there is a sudden change. So that value of the velocity also changes at very sudden levels, where this transition is smooth. In case of, as we have seen earlier, in case of step response, the transitions are not generally as smooth. Now, the smooth transition in the right top corner, you can see the video and observe it very carefully. You'll see the smooth transition of the velocity of the servo system. Please observe the velocity marker, that is the digital display that is there. If you cannot perceive the changes in velocities with your bare eyes, I think that marker will be very helpful. Now, let us see what happens when we change the frequency from 100 millihertz to say 10 millihertz. So we decrease it, say, oh, 10 millihertz creates a certain problem with in the simulation mode. We can change it to 20 millihertz and it will be smoother. So let's see what happens. You can readily see that the output is being updated more slowly. It's being updated more slowly because since the frequency is low, 20 millihertz, the time period is high. And since time period is high, it will reach to the peak slowly and come down to zero value it slowly as well. And it will reach to the bottom peak, that is the highest speed, in the opposite direction slowly and come up slowly as well. If you look at the video on the right hand corner of the screen, that is actually captured for one millihertz in the lab. You can see that it takes a lot of time. It takes about a minute or so in order to to complete complete rotation, or in order to reach from zero speed to the higher speed, then to zero speed, and again negative higher speed, and again to zero speed. While you're watching the video at the top right corner, be very careful to look into uh, the velocity marker. You see the gradual rise in velocity, which was very abrupt in case of step response. In case of sinusoid response, the velocity marker is rising or changing very gradually. So this is what we get when we look at we look at 20 millihertz signal. And now what we can do is we can actually increase the frequency. So let's increase the frequency from 20. Let's increase it to 1 hertz. 1 hertz. By increasing it to 1 hertz, you see it's very fast. And on the top right corner, you'll see the video where you'll see it's reaching the highest speed in one direction very fast and reaching the highest speed in the opposite direction also very fast. This is because higher the frequency, lower the time period. Low time period means fast operation. Now, from the video, it's really clear how the black box or the servo system operates at different frequencies. Now, let's move on to what we need to do in our experiments. What we need to do at first is we reduce the frequency to 20 millihertz. We will not be using 10 millihertz because it creates some problem. So you'll go into the data sheet. There you will not be using the 10 millihertz one, we'll be using 20, 50, 100 and all the other things. So we start with 20, or let's since 20 will take some time, let's just to speed up the process and show you what you need to do. Let's start with 100 millihertz. So after going to 100 millihertz, we'll freeze it and we'll wait. After waiting for some time, we'll see here frozen and we click on. At first, what we do, we find out the input magnitude, input span. Input span is 6. Then we'll determine the output span just like the previous experiment. Their output span is 5.5, just like the previous experiment. Then using this D, what we'd do is we'd find the peak of the second one, peak of the second wave, that is peak of the output wave. Now it is to be noted that the peak of the input wave was actually at 90 degree and the peak of the output wave is as you can see it's 98 or 99 degree wherever you put it. So it's not 99, it's actually somewhere in between 98 degree. I can do this and increase the time frame and then find this. So it's about 98 degrees. So what do you do? We put output volt peak to peak 5.5 volts. Phase lag is phase lag obviously uh, a 9 degree lag. So we put it as minus 9 degree. Why is 9 degree lag? The input is 90 degree, output is 99 or 98 degrees and 98 degrees. So phase lag is minus 8 degrees. And amplitude ratio. Amplitude ratio is our uh, the plan gain, that is amplitude ratio is equal to output span divided by input span. So from that we find amplitude ratio, and at last we find amplitude ratio in dB. So 20 log 10 base log amplitude ratio, and here we get the unit as dB or decibels. Here it is a pure number. Here we get in decibel unit. So by this, in this way, we fill out the entire form. From we take 100 millihertz and then we again start it. We change it to say 1 hertz. Uh, okay, it's not operating properly in 1 hertz for some reason. So if, for example, we'll try to take all this data, but there are certain glitches sometimes, and if it doesn't work in that frequency, we will change the frequency. For example, it sometimes works in 90 millihertz and sometimes it doesn't. Sometimes it works, sometimes it creates problem. But at present, it's working at 900 millihertz, it's working at 1 hertz. So if time constant is into 1 times, it is not supposed to create problem. So in all these cases, we'll be following all these cases. We'll be stopping the curve. We'll be determining the output volts peak to peak, and we'll be determining phase lag peak to peak. Phase lag. What will happen? The value of phase lag will be low when the frequency is low, and the value of phase lag would be high when the frequency is high. High means negative, uh, high in magnitude, but the phase lag is always negative. The value of phase lag will decrease in the negative direction with increase in frequency, and the value of the output voltage will also decrease. Now, what happens is the next thing we'll do is we'll take a semi-log graph paper. So you can do it in Excel or MATLAB, whatever your choice is, or you can do it by hand and click a photo and send it to me, no problem. So we'll take a semi-log graph paper. Semi-log graph paper is a graph paper where x-axis is logged. X-axis is log here, log of frequency actually. So what, taking a semi-log graph paper, we'll see at lower frequencies, the amplitude ratio is almost constant. And as the frequency rises, the amplitude ratio gradually falls. So we'll see a graph similar to this. Maybe it won't intersect, but we'll see a graph similar to this. This is our amplitude ratio graph. In the same graph paper, we plot the log f and we find the angle. As you can see, at initial stage, the angle would be 0. then angle would be gradually declining, then angle will again be constant. So this is our amplitude graph. This is our phase graph. So we have to draw these two graphs. So x-axis is log of frequency, y-axis in this case is the amplitude ratio in dB, and in this case the y-axis is angle. And obviously angles will be negative because it's phase lag. Now, after we have drawn these two graphs, from these two graphs we'll be able to determine the actual gain. So what would the gain be? The gain would be at the initial stage, that is at low frequency, you'll see that amplitude ratio is constant. Amplitude ratio is constant, and this value is the gain. So you won't take it directly from here because this is in decibels. What you do is when you fill out the data table, you'll see that this column over here, initial 2 or 3 values will be constant. So you'll take these value as gain. That is, suppose it's 0 0.9, 0 0.9, 0.9, whatever. So that is your planned gain. So planned gain is this value, the highest value of the amplitude ratio. And the second thing that again I'm saying, this amplitude ratio that you're saying is actually plotted in dB, but the gain would be in natural units. So gain will not be in dB. So you have to be very careful that you either take it from the table or you change it as or you convert from dB to natural unit. That is to a number. Then the next thing is we have to find the break frequency. So there are three methods of finding break frequency. First break frequency finding method is minus 3 dB point. So what is minus 3 dB point? Whatever this is, it has a dB. For example, let us suppose it is 10 dB. Suppose, just example. If 10 dB from the peak, we'll find the minus 3 dB point. That is minus 3 dB would be 7 dB. So it is not negative 3 dB, rather it is the highest value of amplitude ratio minus 3, whatever that is. Now this minus 3 dB line, so this is our minus 3 dB line. This minus 3 dB line will intersect with the amplitude ratio curve at one point. The frequency at that point, F, this is the break frequency, F1. So F1 is the break frequency from minus 3 dB point. So that is the first method of determining break frequency. The second method of determining break frequency would be, let's change the color for better understanding. You draw a tangent here and you draw a tangent here. These two tangents intersect at this position. From this position, you draw a perpendicular. So the frequency of this point, F2, this is a break frequency, and the method is called slope method. So from the first method, minus 3 dB method, we find our break frequency as F1. From the second method or the slope method, we find break frequency as F2. And there is also a third method which is called minus 45 degree method. So, that is derived from phase plot. So this is the phase plot. This is 0 degree. So at this point, suppose we find minus 45 degree. And this minus 45 degree line will intersect with the phase plot, and if we extend the phase plot, if we draw a perpendicular on the x-axis, we'll find a frequency. So F3 is equal to the break frequency from phase plot or minus 45 degree method. So like similar to the process of finding tau, we have a process of finding three processes of finding f as well: minus 3 dB, slope, and minus 45 degree methods. We find the average of all the three methods to find the break frequency. One thing is to be noted that this break frequency is in the unit hertz, and our tau is equal to 1 by 2 pi f. 1 by 2 pi f. Now, this F is equal to the break frequency, that is average of F1, F2, and F3. From that, we get the time constant. So, what we're doing, in this experiment, what we'll do is first primary target is filling up these data table. We'll not be using 10 millihertz. We'll be using all the other frequencies and fill up the data table. And after filling up the data table, we'll readily obtain the amplitude ratio and in natural unit here and in decibels in the last column. Then we'll draw a plot of in a semi-log graph paper. We'll draw a plot where x-axis is a frequency in log and y-axis is the amplitude ratio in decibels. Similarly, we'll draw a phase spectrum in which x-axis is frequency and y-axis is the phase lag. From that, we'll use the three methods: first slope method, then minus 3 dB point, and then minus 45-degree method. From three methods, we'll find three break frequencies and we'll find the average of break frequencies. From that average, we'll find tau is equal to 1 by 2 pi f. From this formula, we'll be finding the time constant. Now, what we'll do is we have Kp and tau from experiment 1 and we'll have a different set of Kp and tau for experiment 2. Then we'll compare these two Kps and taus and uh, find if there is any difference, and whichever comes most close to the values that we are supposed to get. Whenever you perform this experiment in this report also, you'll modify the Kp time constant and Ki in the same way as you did in the report of experiment 1. So I'll not repeat the process again. You'll modify this in the same way and you'll find all the graphs and we'll find all the outputs. You'll fill out the data table, you'll answer the question, and you'll give us screenshots of all the calculations that you have taken so that we understand that you have actually performed the experiment on your own and the result that you're using is correct. So that's all for this experiment. In these two experiments, we have learned how to model our plan, and in the next experiments, we'll be learning about the principles of feedback and we'll be learning to design controllers. Thank you.